Hi everyone, and welcome to another Q&A episode. The question for this week is a colleague said that we should group similar data types together in DBs for optimal usage. But what does he mean by this? Now, straight away, I went to the optimized or unoptimized data, which you can find by right-clicking on a data block or a function block and changing this optimized block access to either on or off. And we're going to leave it off because I think what he's actually referring to is the offset here. So here I have a data block with booleans 1 through to 10 with 2 integers in the middle and then 11 through to 15. And you'll see that we have an offset here with nothing there because I haven't compiled yet. But when I do compile, we see these fill up with their offset values. Now notice we get to 1.1, which is byte 1, bit 1, and then we jump to byte 2, 4, 6, and then continue. And that's because these are sat in the middle. So the way TIA Portal works, and a lot of other PLCs as well, is you can't start your offset on a odd number unless you're working with a byte or with booleans that are sequential. And you can only actually do the bit access if you have sequential booleans. So the second that you interrupt that with a different data type, you jump to the next available byte. And that's what's happening here. So I guess what your colleague was saying in your question is we should try to avoid doing stuff like this. So if we were to change this to something like this, for example, where the ints are at the end and we have a clear run of uninterrupted booleans, when we compile this, we end up with a much nicer offset that has taken up less space because we have filled as much space as we can. We're not making this additional jump to another byte. So when we were in the middle here, we would have had to jump from byte 1 to byte 2 and then jump back to another byte after these ints to continue our booleans, making the whole sequence longer. If I do a bit more of a complicated example, we can see the effect on this can run away quite considerably, especially if your DB is really, really big. So looking at this example here, we have a similar thing of a run of booleans with a LReal sat in the middle, and then quite a considerable jump here because of the size of an LReal to bool 3, where we do 2, and then another integer, a byte, an integer, some more bools, and an integer, which means that our final offset starts at 20. But just some subtle changes that we could make, like moving the real to the end, so it's well out of the way of the booleans. These dragging of variables into your ball could do with a little bit of work. Sometimes it's really difficult to put something at the end. But if I then compile that, we can see that we're now ending on 12. Bearing in mind that an LReal is 8 long anyway, that gives us a block length of 20, but before it was 22. So we've saved 2 bytes doing what we by moving this real here. And then we can see that we stop at 0.4 to jump to int 1. So if we move the booleans so that they are all next to each other and do the same again, we can see that we are finishing on 10, but we have a gap here where we're jumping from what would be the start of a new byte, because a new byte starts after 0.7 when you're working with bits. If we were to put a byte in, which is only 1 long anyway, that should slot in as a odd number, which would save us 1 byte at the moment. So we start at 1 here, move to 2. There's no wasted space between any of this. There's no wasted space here. There's no wasted space between this int 2 and byte 2 because int is too long, which brings us down to 6. However, we know that byte is only 1 long, and that gives us a spare byte between byte 2 and real 1. But there isn't anything we can do about that because we only need 2 bytes. We don't need anything to fill that space in. But understanding what's happening is quite important, because if you did need to slot something in, and you don't have capacity, I mean, this is quite trivial for what we're talking about, but if for whatever reason you couldn't expand the length of this block, you do actually have a spare byte between these two if you happen to need a byte. From an aesthetics point of view, it would be nice to move that byte underneath this one, and if we compile, nothing's changed. However, what we have done is, if we need a third byte, so if I add byte 3 to the end, actually, whoops, move that up. So we'll add it to the end. I've just noticed that this is a integer. It shouldn't be, but it won't change anything because of the byte offset anyway. So we're finishing on 16 here. You can see from 8 to 16. That one's an int as well. Sorry, I'm this one up. Let's compile again. It doesn't change anything though, because we can't start on a odd number. So, but if I put this byte 3 here, this one should start on an odd number because it's only one long, which it does. So we're back down to the original LReal on an offset of 8, even though we've added a byte in. And hopefully that demonstrates what your colleague's talking about, which is, it's not optimized data, it's optimal organization of your data, which is two slightly different things. If we're talking about what Tier Portal does on the optimized data here, optimized block access, that's slightly different. It does ultimately do the same thing, where it bundles up the data in here in a way that optimizes its usage, so you don't end up with gaps and things like that. But it also fundamentally changes how you access this data. So there's certain functions and methods that you can't utilize on data within a optimized block. My personal preference is to do things my way, and I don't use optimized data. However, that also causes issues with reinitialization of data later, because you can't use memory reserves in non-optimized data. So there's trade-offs for it, but I believe what your colleague was talking about is actually making sure we don't just create as we build and leave it in an order that really wastes a lot of the memory.